the corresponding form so that we can proceed with finding the parameter values that will best fit your curve. So with this thing, on top of this, we are going to discuss some extension of the method that we discussed earlier, and also try to give some general overview. And lastly, we'll try to give some hint how the nonlinear fit can be made with the help of numerical method that we studied earlier. Actually, the thing is that the curve fitting technique is grouped into a nonlinear category. Just as you have our numerical data there, just to calculate the values of the unknown coefficients. But in doing this, you see that we will be obtaining some form of equations, simultaneous type. Then we can deploy whatever the method we learned earlier for solving simultaneous equation here to find the solutions of those resulting equations. Along with this thing, we can also deploy some iterative technique there so that those things can again be determined iteratively, like your Newton method or something like this that we'll discuss there. Then we'll, if time permits, then we'll go to a new topic. This is what our content today. Let me discuss about first multi article. In our earlier discussion, actually, we have started with a linear regression. That means if we have a distribution of data given, then we can, what we can do, we can fit it by a straight line that will have two parameters there. But if we have our linear data, then what you can do, you have your two different approaches to proceed with. Number one, you can, if your equations allow you to convert it into an equivalent linear form, then we can use that. I have discussed earlier that if we have an equation, something like this, that we can use to fit a curve e to the power, say, beta x, then resultantly this curve can be shaped into a form, say your natural logarithm y is equal to ln a plus b into ln x. I hope we have discussed this issue earlier, isn't it?
Yes, sir.
But the thing is that this is also an equation of a straight line, but not in xy plane, but it is in the plane of log y and log x. Okay, you can change this variable to y and this variable to capital X. Then we can follow our linear regression technique that we followed earlier. Then we can find the solution. Okay. So this is one approach where if your fit equation can be transformed into an equivalent linear form, then we can use it. But in some cases, it may not be possible. For example, say, if we have a function that needs to be fit in this way, a into 1 minus e to the power, say, minus bx, can we convert this function into an equivalent linear form in this form so easily?
No, sir.
You can try, okay? But if not, then how to proceed with, okay? That particular thing I will give a stress because most of the practical purposes will encounter this type of function because this type of function has some, this type of situation behavior, okay? Like the functions that I discussed earlier, something like this, say beta x divided by alpha plus some x or something like this, okay? So our discussion now, the extension of our linear regression to some what we call generalized form, we call it polynomial regression. Okay, that means your curve can be, your data can be such that it can be fit, for example, by using a polynomial. Okay, if we have our data, say, varying in this way, okay, for example, something like this, what we can do, a straight line fit will not the best fit, okay? Then what we can do, we can increase the degree of a polynomial so that the fitting will be, the goodness of the fitting will increase. So in this sense, what you can do, you can choose a function something like this, a0 plus a1x plus say a2x square. Can we do that? It becomes a quadratic function, isn't it?
Yes, sir.
Then it will have a parabolic type nature. So a straight line fit will not be the best fit for this problem. Then this equation can fit a bit better than what we can expect for a straight line. So in this case, what is happening? That the process is exactly the same. What you need to do, you have to derive the normal equations. Then in this case, you know how many normal equations we will have? We will have three normal equations, isn't it?
Yes,
That
sir.
will obtain from what? By calculating, for example, this quantity SR that we define as what? Sum of, say I equal to 1 to n, it will be equal to yi minus a0 minus a1 xi minus a2 xi square, isn't it? And it will be whole square.
Yes, sir.
Yes, sir.
Then you differentiate this because now your SR is the function of a0, a1, and a2.
A2.
Then how many times you have to differentiate? You differentiate it first DSR with respect to a0, set it equal to 0. Then you differentiate DSR with respect to a1, set it equal to 0. Then you differentiate SR with respect to a2, set equal to 0. Now how many equations we will have?
Three questions.
3.
You will have three equations there, and those three equations can be solved simultaneously to find these three unknowns. The resulting technique is same, okay? You look at in equation 1.79. Then you will find a very general form of this equation. Then you can just use this equation for even for your higher order of polynomial. It would be equal to n a0 plus sum of xi a1 plus sum of xi square a2 is equal to sum of y. In the earlier case, this term was not there. And the second equation would be equal to sum of xi into a1 plus sum of xi squared into a0. This is a1 plus sum of xi cube a2 is equal to sum of xi yi. And the third equation will be equal to sum of xi square a0 plus sum of xi cube a1 plus sum of xi 4 a2 is equal to sum of xi square y1. Okay. So in this way, you see that you can then you solve for a0, a1, and a2. That will give you the best fit of your curve. Okay, so this is the extension of your linear least square curve fitting to a quadratic equation. If your order is say 3, then you can easily see that you can add another constant there. Then you have to solve 4 by 4 matrix for your solution. Your numerical technique will involve here. Okay, just for finding a0 to a3, you can deploy any of the techniques that is suitable to find those unknowns. Now we have another thing there that is also a bit extension of your linear regression, where multiple variable can be there in your as an independent variable. That means some thing can vary with what two independent parameters. So in this case, you will see that the same technique can be applied there just to find the regression coefficients. I am leaving this to you for your self-exploration. It is article 7.3, okay? If you have your problem in understanding, you raise the question, I will discuss on it in the next day, okay? Now we'll be generalizing the thing. That generalization is needed. The reason is that if we have our system that is linear in particular, and we want to deploy a numerical technique there for our solution. In such cases, this generalization technique will help us to proceed systematically. For this reason, let us talk about, I will share your book a bit later. Let me talk about the general behavior of your regression. Actually, the thing is that what we are doing in our regression, that we are, for example, assuming a function, something like this. For your linear regression, it is a1x, okay? If we add another term there, it will be quadratic. Then we can add another term there, cubic polynomial, okay? then in the same sense, we can add many numbers of term there. Then even if you add many numbers of term there, still an error term will be there. That error should be minimized by calculating the difference between minimizing the square of the difference between your estimated value and the actual value. Now the thing is that this quantity X is actually one thing. Another issue, what you have seen in your Fourier series, that if we have a function Y, that function can also be approximated as A0 plus sum of say n equal to 1 to infinity an cosine omega 0 nt plus bn sine omega 0 nt. Okay, theoretically, we need infinite numbers of harmonics for our representation. But can you calculate up to infinity in practice?
No, sir.
You
No,
cannot
sir.
calculate infinity in practice. That means you have to use a finite numbers of terms, say, hey, m, for example. Now, how to choose m? This is the actually Fourier series is based on LMSE, that is least mean square error criteria, the similar criteria that we are using for least square curve fitting. For this reason, already your error is minimized with respect to your square of the error to determine your A0, AN, and BN coefficients. But here in this case, when you are using finite numbers of terms, this is another approximation you are just imposing on it. The reason is that we cannot handle, for example, infinity. If we cannot handle infinity, for example, in our practical numerical computation, then what you need to, you have to truncate. You have to truncate this infinite series after a finite numbers of terms. But that truncation is possible, certainly possible. The reason is what? The reason is that we know that your coefficient an and bn both is the function of the harmonic number n, okay? As the harmonic number increases, the magnitude of an and bn increases or decreases. Didn't you solve any problem in your mathematics course to find your an and bn? Did you?
Yes, sir, we
No,
did.
sir, we did, sir.
If you did this thing, did you observe that in what ways these constant an and bn are changing with n?
Yes, sir.
How? The problem that you solve, okay, can you recall it? Okay, what will common sense tell you? That in what ways your A and Bn should decrease or increase?
So I think increase.
It will increase. Look, mathematics is not something like that. You are not a mathematician that you have to learn mathematics in a way that mathematicians usually do. But what you need to do, you have to find some reasoning, okay? You see that if this is an infinite series, then by using your simple common sense, you can easily say that that truncation would be possible only when for higher values of your n, the contribution of this series will be negligibly small. Only when you can truncate it. Otherwise, can you truncate it?
No, sir.
No, sir.
So this is a converging series. Your Fourier series, like Taylor series, okay, it is always converging. After as you add more numbers of terms, gradually the higher harmonic will be contributing significantly less to your approximation, so that you can discard them. And this is also true for your practical purposes. Okay, we usually start our Fourier series analysis by using a simple function. Probably you cannot expect any more simpler function than this function in order to study your Fourier series. Okay, this is the most simple and most elegant function by which you can study your Fourier series. Your common sense will tell you that if we want to generate a square wave by the Fourier series that contains an average value as well as some cosine and sine terms, then will you have any average value for this function? Will there be any A0 constant for this function? If we take the average value over one period of this function,
Say it will be 0.
It will be 0, okay? Actually, the thing is that there exists a test of the symmetry of your function that will tell you which constant will exist and which are not. Did you study the symmetrical condition of a function like even function or odd function?
Yes, sir, we did.
Yes, sir.
You did, okay? Is it an even function or odd function? How to test it?
Sir, if f of minus x is equals to f of
Okay,
x,
fine, very good. If, for example, say this is your function, okay, that means if your xt is equal to x minus t, then we call it even, isn't it? How to test it? Okay, consider that this is the point t, okay? You have your value of the function is equal to a. And you just go in the opposite side of minus t, then you will find a value equal to what? Is it not minus a?
yes,
That
sir.
means this,
Yes, sir.
this is not satisfied by this function. Rather, this is satisfied. Xt equal to minus x minus t, isn't it?
Yes, sir.
Yes,
So
sir.
this is the test of an odd function. Now, if you have an odd function actually, then a0 doesn't exist. A0 would be equal to simply 0. Then your an is also equal to 0. Okay, you will have only bn. That means your bn is equal to 2 divided by t integration minus t by 2 to t by 2. It is your xt into sine n omega 0 t dt. Okay, your omega 0 is equal to twice pi over t. And you see that for n equal to 1, actually, you see that it will be a sine curve. And if you want to plot this sine curve over this curve, you see that your sine curve will be looking like this. And it is also very similar to your curve that you are using. It is also alternating, but it is a first order approximation. Then on top of it, if we add a curve, something like this, I don't know whether you studied in this way or not. Okay, if we add a curve here, for example, in this curve, then how it will look like? Say your green curve is added with your blue curve. Then will not your curve will be looking like something like this. You got it?
Yes, sir. Good.
Now, if we add more numbers of terms, for example, you see that your curve will be something like this. Okay. Although it is not rectangular, but going closer to the rectangular, you can check it by your own. Very simple something, okay? You pick this function, you know the value, choose a value of a and t, then you plot it, write a few lines of MATLAB program to add them, then you can easily observe it. Now, why I'm bringing this example to you, the reason is that, as you see that if your first is for n equal to 1, then your last one for say n equal to 3, your third curve was n equal to say 4. You see that if the higher harmonics amplitude a bn for n equal to 2 to 3 onwards are not decreasing progressively, then if you will add them up, then the total curve will be going above a, isn't it?
Sir, can you repeat?
This is very simple thing, okay? For example, you are obtaining this curve by adding how many curves?
Sir, 2.
1, 2, 3, 4, okay, so generally, okay? If we add, for example, many curves, then you will see that your thing will be looking like this, okay? Say you add 5 curves. Okay, not only this thing, you see that this symmetry condition will again tell you that what harmonics will be present. In this case, the odd numbers of harmonic will be the useful harmonic. So your n equal to 1, n equal to 3, and n equal to 5 will be there. So if we add, for example, n equal to 1, n equal to 3, and n equal to 5 in this curve, you will see that your curve will be looking like this, okay? Now, what your common sense will tell you, that if this blue curve is the first one for n equal to 1, with amplitude, some amplitudes are there, and you are adding on top of it the other curves for n equal to 3 and 4, then in terms of the magnitude of bn, okay, if your magnitude of bn is equal to say 2 for n equal to 1, can you expect that your magnitude of bn would be equal to more than 2 for n equal to 3?
Yes, sir.
Yes, sir.
Yes. This is what I am telling, okay? It is not yes. If this is yes, then what will happen? If you add those things up, say for a equal to 3, you are getting this thing. Then what will happen? This curve will overshoot, okay, the original one. And in this case, what will happen? You cannot truncate after finite numbers of terms. If your amplitude becomes higher progressively, okay? You see that if you could, I don't know whether you have solved the problem practical there in math or not. You see that that value of an or bn, all are the inverse function of n. The least in variation will be equal to 1 by n. In some cases, it will change 1 by n square. In other cases, it will change in this way. That means if n value is larger, the amplitude will be progressively smaller, so that you can truncate your curve after finite numbers of terms. Actually, my intention was not here to discuss about this thing. The reason was actually I want to just discuss here. That means if you have a function or a data that you want to fit by using some mathematical functions, your data can be non-periodic type. In this case, a polynomial variation can be adopted there. And if you have a periodic data, in this case, you can deploy your Fourier series to fit your data. Now, the question is, in generalizing your least square technique, we usually say that this quantity x here in this case, say x1, x square, only x cube, whatever it may be. In this case, cosine n omega 0 t or sine n omega 0 t, all are called the basis functions, because the nature of the functions is already known to you and you have chosen that function independently, okay? Now your task here in fitting is to determine the value of the constant a0 through n in both the cases, so that the error will be minimized, okay? That is what the thing. For this reason, in your book, you see that in article 17.4, when it has been generalized, rather than choosing any definite function, a basis function of general form has been chosen. A key problem taki, who is speaking there? I hope you can see it. Already we have discussed the thing. This is there. You have a look. This is what your generalization form, okay? We have discussed this thing already. So here in this case, instead of using x or sine or cosine, a general format of the function z0 and z1 through zm is introduced. You see that in your least square, what we usually do, we have to calculate this value yi minus, say, this a0, z0 through am, zm. Okay, this is what your error, ei. That error is to be calculated at each data point, isn't it?
Yes, sir.
Then you have to square that error and sum. That is what we are doing this thing, okay? And that is what your XR. Then we optimize XR, okay? So that the corresponding, because your SR would be the function of what? Your SR will be the function of A0, A1 through AM, isn't it? That means you need M numbers of equation there, but not always that you can find that derivative so easily to put into the equation into the matrix form. So in this case, some other technique will be followed, but the general case can be put into the matrix form with the assumption that the element of the matrix are calculatable, okay? Okay, just a systematic look in your text, you see that the things are not simple, okay? Whenever we have a function, then you see that the equation that you have seen earlier, equation number 17.23, can we put, for example, it into a matrix form? we can easily put into a matrix form. You see that
Yes,
if we
sir.
define a matrix Z, that matrix is this. This will contain the value of your basis functions at the data point. It will be very clear when we will be talking about with an example. Okay. Then you see that this, in general, this matrix will have a dimension depend on the number of unknowns we are using there. Accordingly, the dimension of your matrix J will be fixed. And you see that your Y matrix, that means the predicted value of your output, is actually a column matrix. So in the transpose form, it can be written in this way. Similarly, your coefficient matrix, the unknown one that we need to determine, will also be a column matrix. Your error will also be a column matrix. Then this equation SR, all I have already written. This is what the equation you need to minimize. Without going to mathematical rigor, we can easily derive, for example, the matrix equation after optimization or taking the derivative with respect to the unknown coefficients A. This can be put into this matrix form 17.25. What we need to do, this form is an established form. You do not think about that there exists any confusion there. So this equation is actually the general form we can solve. The objective here would functions are determined. Then we can find Z. Once your Z matrix is available, transpose it. Then transposition, and because Z matrix is the key matrix here to be determined actually. Then after having this thing done, then actually this will result in a simultaneous equation, a set of simultaneous equation, isn't it?
Yes, sir.
Yes, sir.
Because Z, if your Z transpose is a metric, if they are a square metric, then dimension of the both transpose, for example, will give you the same dimension of the metric. But sometimes if you have two unknown, then if you have n numbers of data points, then your Z matrix can have the dimension to your first index signifies column or row?
So row.
Row. Then it will be equal to 2 multiplied by n matrix. Okay. Then if we want to, because your matrix cannot be multiplied if they will not satisfy certain condition, isn't it? Can you multiply randomly?
No, sir.
No, sir.
Then you need, if you want to multiply with your Z, that multiplication would not be possible because this is not a square matrix. Now what you need to do, you have to transpose the matrix to make it. Okay, if you transpose it, the transpose matrix will have a dimension equal to 2 by n. Isn't it?
Yes, sir.
Yes, sir.
Then we can easily find what will be the resulting matrix. So in this way, we'll proceed. Actually, you know the matrix algebra. We need not discuss much about it. But okay, it will be clear. The mathematical thing is actually when it is not established by an example, it is not that much clear to you. We are not mathematician. So our example will make us to learn it. Okay. So after having this thing solved, you will find the solution of A. Now the thing is that we are not going to many of the things that is related to theoretical aspects. Let us start with, okay, this example has been solved with this equation. Okay, try to resolve it, but we will be giving some an introduction so that both of the thing will be covered there. Okay, just in article 17.5. We will be doing with Londonian something and solving one example that will involve all the equations that we used earlier, okay, in the matrix form. Just a simple thing, okay, you will understand it. Now tell me that is it not the equation very similar to the current flowing through an inductor in an RL circuit or a voltage across the capacitor when it is charging by a DC voltage, isn't it?
Yes, sir.
Okay, fine. Then if you are in the laboratory, for example, you have a device to measure, for example, your capacitor voltage, say VC, starting from 0, then you can measure it in this way, okay? Because your measurement may not follow exactly what is there, isn't it? If this is what your measured value, then you can choose, for example, you know the characteristic how the things are there. Okay, then you can choose your function, say a0 into 1 minus e to the power minus a1 into x to feed this function. Then what will happen then? After finding the value of a0 and a1, those things are actually in practice it has a relationship with what? Circuit parameters and input, isn't it?
Yes, sir.
For a capacitive circuit, what is your A? What two quantities are involved in A0, and what quantities are involved in A1? First year Parashina. Is it not your A0 equal to E divided by R?
Yes, sir. And A1 is lambda.
And your A1 is equal to 1 divided by RC. Is it?
Yes, sir.
Yes, sir. Time constant.
It is not time constant, inverse of time constant. Time constant is RC. A1 is not time constant. Time constant has the unit of second. A1 is the unit of 1 by second. Okay.
Second.
So these are practice. Okay. This is practical. In this way, you have to relate your understanding with your discipline. Okay. Otherwise, a thing will not be interesting to you. Okay. Similarly, if you think that it is the current flowing through an inductor, then your A0 will be of same thing, but this alpha A1 would be equal to what?
R by R.
R by?
R by L, sir.
Okay, this is also inverse of time constant for your RLC circuit. Okay. Similarly, for the mechanical engineer, if they are doing it this thing, okay, in this case, you can think that this situation is something like this. Okay, you have a mass M. This mass is, for example, placed on a floor, and a force is applied to it to pull it. Then what will happen? Your mass will begin to displace from this location in this direction. Okay. If you want to solve it for your velocity, then what will happen? The velocity equation will involve your force is equal to your m into dv by dt. This is what the another force, and another force will be lost in your friction. This is what your differential equation. Okay. Then if we solve for velocity, you will see that your velocity will take this form f divided by b into 1 minus e to the power minus b divided by m into t. This is what the velocity of a mass. If your mass is displaced on a floor with having a friction in it. So you see that mathematically all this equation belongs to the same category. Okay, they are nonlinear and having this type of saturated nature. Okay, but I will not relate this thing totally with what we call saturation that we observed in the case of DC machine for induced voltage or in BH curve for magnetic circuit. The reason is that the situation is a bit different, where this saturation will not follow exactly this curve. Okay, in the last class, probably I named an equation. The spelling was incorrect. Just I am correcting the spelling for your reference. If you want to explore further, you can do it. Without inquisitiveness and further exploration tendency, you will never be the student of this age. Be careful about that. So try to change your attitude. Okay, explore something, feel interest in doing something. So the king that equation was actually Froelich equation. That equation was derived in 1997. You can easily say that at the beginning when your electrical machines have been designed. But nowadays, still this equation is relevant. Not only that, by using tan H curve, you can do that. Do you know how your tan hyperabolic varies?
Yes, sir.
Sir, the 10x.
Tan hyperabolic, not tan.
Oh, no. Yes, sir.
Try to find that that how saturation curve can be generated by using tan hyperabolic function. Try to explore. The reason is that actually we are having something with us that we sometimes call inbreeding. Do you know what is inbreeding? You are recording my class, you can record it, no problem. But be careful about this thing. This is a private talk between the student and teachers. You got the thing?
Yes, sir.
And that cannot be abused. Be careful about that, okay?
Yes, sir.
So the discussion is not for any criticism. The discussion is for what we call producing some awareness about the learners and awareness about the managers. Okay, the reason is that I usually talk about this issue to many platforms. The reason is that we call one thing called inbreeding. Do you know the term what is called inbreeding?
No, sir.
Inbreed means what? Breed means produce. Inbreeding means you are producing something by your own with the help of some seeds that you are also producing. Okay, you know, if I ask you one question, okay, that you see that many our respected fisher, what we call farmers, because farmers are to be respected. Okay, in India you see that farmers are regarded as God because they are producing your stuffs for your living. Although Almighty Allah knows everything, but on this earth, okay, you are farmers are the one who is just making just what you call for your food, for your other stuffs. Now you see that when a farmer cultivate, for example, fish in his pond, you see that if you go to your market, now if you want to buy fish in this season particularly, you see that all fish contains egg in their belly. Isn't it?
Yes, sir.
Have you seen it?
Yes,
Yes,
sir.
sir.
Okay, fine. Then those fish have been caught from the pond of a farmer, say. Then in the next year, when he again try to, for example, give some what you call young fish there for cultivation, why he is not using those fishes that that has some egg? They can also hatch and produce, for example, your brood or something like this. But they are what they are doing actually. They are going to the hatchery, and again they buy new fish, for example, and they nurture it in their pond. The reason is that this is the thing, the effect of inbreeding. Okay, that means if he use the same thing that he is producing as the seed for his subsequent yield, then what will happen? His production will be decreased in such a way that his will not be benefited. Then he will be a great loser. For this reason, he do not want to use this risk. The reason is that when we are in a confined environment, having something cultured there, you do not have any experience of your outside, then what will happen? It is something like that, a frog in a well. Do you know the thing? A frog in a well?
Yes, sir.
কূপের মধ্যে কোনো ব্যাঙ, বাংলায় যেটা বলে।
Yes, sir.
If you are in a frog in a well, okay, you do not see, they did not see anything around you other than what is there inside the well. Then you will never be able to explore anything and never be able to give vision to anyone, because your vision is already narrowed, glaucomic vision, already narrowed. For this reason, actually, we need education, a diverse. If a university has diverse students of different discipline, different culture, different understanding, if your teachers will have different types of learning from different great universities, then what will happen? They can give you the vision so that you can move forward. But unfortunately, in this country, this is not happening. If you go to the United States or even in many countries, they will not take any of their fresh graduate, for example, as their teacher. They always say that you go outside and see something. What is the difference between what you have learned in this university and what others are doing? Then you come here after 3 or 4 years, then we will take you. Otherwise, inbreeding will be there. You got my point? For this reason, actually, if you cannot change your vision and expand it, the horizon of learning, then your understanding will never be complete. Okay, be careful about that. This time it is very, very relevant. Vision is very important. Okay,
Yes, sir.
if you cannot set your vision, then how you will proceed? So that is what I am telling you. Whenever you are learning something, you did not learn want to understand everything. But whatever you are doing that is very relevant to your field, you try to learn it completely, try to relate the thing completely with your understanding only when you'll understand the importance of learning. Okay. So you see that that equation is mathematically a general equation. But if you want to relate it with our field, many of the practical observations can be related to this equation. Okay. So with this thing, let us proceed with. Okay. Now the thing is that as one technique we already introduced, that if you have a nonlinear variation, that nonlinear variation can be fit by using some exponential or power curve, and those exponential curve can easily be transferred into a linear form by using some transformation technique. Then linear regression technique is good. But unfortunately, if we have some functions, those functions are so not complicated, but they are not well posed in a sense that they can be converted into a linear form by simple transformation. So in this case, what you need to do, you have your one options there. You have to apply some logic, the technique of solving nonlinear system of equation that we learned our earlier subject by using iterative type technique. And nowadays, we have another discipline they are called optimization. In your course, you have a topic, introduction to optimization. I skipped this thing at the beginning. The reason was that it needs some understanding of some other thing. Those things are yet to be touched. But whenever we'll have the thing with us, again, we'll be going back to our optimization. Just to give you some introduction, that may not be what we call to that extent in this case, extensive, but still that introduction will help you to proceed further, inshallah. So in this case, what you can do, very simple logic, okay? Do not get panicked, okay? Just simple logic. You see that your iterative techniques are actually developed by using simple logic. You see that in our case, our objective is what? We have to determine the constant A0 and A1, isn't it?
Yes, sir.
Yes,
We
sir.
have to find A0 and A1. Those values will be optimally set so that that curve fx will fit best our observation. Okay. Now, in our least square fitting, we derive normal equations, then we solve them to find A0 and A1. Normal equations was derived by a criteria. We call it least square error criteria. So in this case, what we can do, in the same way, we can obtain the normal equation, no problem. But in the iterative cases, what we usually do, we have to, for example, start with an initial value of A0, say A0, 0, and A1, 0. This is what your initial value you have chosen as an estimate. Next thing is what you calculate, for example, the value of your error with the help of these two constants. Okay, how to proceed with? Just you calculate your SR by using this value A0 and A1 and use this thing to optimize. Later, again, you calculate your value because you see that your first approximation will never give you the optimum value, or that will not satisfy your LMSE. Then what you need to do, we can derive an equation I will be showing so that you will obtain, for example, a change of your del A0 and del A1, like our Newton-Raphson method or any other approximation method. Then in the next iteration, we will update the value of A0 to del A0 and your A1 to del A0 plus del A1, okay? And that is what the new value in the next iteration, you can call it A01, and this is your A11. Then again, you repeat the same process. Then if in each iteration point, you are obtaining the new value of A0. Then what you can do then, that you can set error stopping criteria for both of your constant. Then if we have our A0, say K plus 1 iteration and A0 for K iteration are available, then you divide it with A0 into Kth iteration, take the magnitude, and you can express it in percentage or normal value, no problem. But this is relative error. We call it epsilon A, isn't it? Absolute approximated
approximation.
relative error. And if this will satisfy your error criteria, you can stop it. Now you see that you have your two variables there. This criteria should be satisfied by both, but you have to seek for global minimum. That means between these two constant, A0 can satisfy these things slower than A1, but you have to wait until A0 satisfy your criteria. Okay, that means this is what the global what you call condition to be satisfied. Okay, not a local one. Local means whenever one variable will reach this condition, you can stop, that you cannot do. Okay, let us proceed with. Okay, your derivation is very simple application of your Taylor series. You see that here in this case, we will calculate the function. Okay, just simple. Okay, just you see that here in this case, actually, we are not talking about X. Okay, we are dealing with A0 and A1, isn't it? These things are variable with us. Then what will happen if we have to approximate this function at a value A0 plus say delta A0? Can we use our Taylor series there?
Yes, sir.
Yes, sir.
This is not the Taylor series. Okay. Now you see that how many variables we have? Two. Then
Two.
this function should be evaluated at alpha plus del A0 and not alpha A1 plus del A1. Okay. Then your two variable up to linear would be equal to, this is for your first variable, this is for your second variable. Okay. Having this thing done, you have this difference. Okay, then you can put it into this form. Then this equation can be put into a matrix form. After having this thing into the matrix form, our objective is what? Our objective is we have to calculate the value of del A, the change of value in you. That means this is what the refinement degree of refinement in your subsequent iteration. Okay, that we want to find. So if we go in this way, you will find that your Z matrix will be something like that, but do not confuse it with your Jacobian. Okay, in your nonlinear system, you use Jacobian for linearization. Okay, this is not actually Jacobian because Jacobian is very similar to Jacobian. Okay, where you have to calculate the derivative of your function in such a way. Now the thing is that how many rows and columns will be there in your matrix. We made a preliminary discussion earlier. Here in this case, you see that we have our two unknowns, A1 and A0. You will have two columns there. Okay, what you need to do actually, from your original function fx, you have to take the derivative of fx with respect to the A0, take the derivative of fx with respect to A1. Then you calculate the derivative of this derivative for each of your data point. This is what this column, first column. Calculate the derivative of your function with respect to A1. This is at each data point. This is how that column. Okay. The number of rows of this matrix will depend on how many data points you have. So if you have your three unknowns there, then what will happen? You have another column will be added with it, isn't it?
Yes, sir.
So your D matrix is this, your del A is this. In this way, we can easily deploy the equation that we derived earlier. Then we can solve it for del A. Your del A would be equal to available. Then we have to update the value of del. Okay, this is what the whole process. I will show an example to you. This example is already there in your book, but we can set our own example from our experimental data, no problem. But you see that systematically how interesting the thing is. But it is actually lengthy. Sometimes this method is called the Gauss-Newton technique. But here in this case, you see, If this method is sometimes actually not converts like other iterative technique, and even it is very slower. For this reason, an optimization algorithm is actually best suited for this type of linear program. In your MATLAB, already proven algorithms are there with they are very efficient. I will show you how this can be used. Even you can check it by writing few lines of your MATLAB program. I will try to give some introduction to you. So now our first objective is what? If we have our function with us, then this data is there. If your data table is there, you have your function, you need to fit. Then our first thing is you have to calculate the derivative of your function with respect to the constants. Okay. We have our two constants there, so our two derivative. I hope everyone can do that. Okay. If we take the derivative of this function with respect to a0, it will be equal to 1 minus e to the power minus alpha x. Okay. If we take the derivative with respect to the second variable alpha a1, what will be the derivative? It will be equal to
A naught.
minus into minus x e to the power minus a1x and a multiplied by a0, isn't it?
Yes, sir.
This is multiplication. Do not confuse it with x. Okay. So this will be equal to a0 x e to the power minus a1x, isn't it?
Yes, sir.
Now next step is what? We have our initial value a0 1 equal to 1 given, and a1 0 the first initial values, okay, equal to 1 given. You can start with different values. Now what you need to do, we have to calculate, for example, the coefficient z, but this z is to be calculated for each iteration. Okay, so in this case we can call it 0. That means for the 0th iteration using the initial value. So what you need to do, we have to calculate the entries in this way. This will be equal to df da0 at x equal to x1. This will be equal to df by da0 at x equal to x2. We go all the way, we have 1, 2, 3, 4, 5 data, then it will be equal to df da0 x equal to x5, isn't it?
Yes, sir.
So in this case, what will happen? In this case, what you need to do, you will need the value of a0 0 and a1 1 to be a1 0 to be used in these two equations. Okay. So your first entry would be equal to then you df da0 a0 at x equal to 0.25 would be equal to 1 minus e to the power alpha 1 first approximated value is equal to 1, and the value of your x is equal to 0.25, isn't it?
Yes, sir.
And the first value of this function will be equal to 1 into 0.25 into e to the power minus 1 into 0.25, isn't it?
Yes, sir.
Yes,
So
sir.
now you change the value of x in both the equation, then you can proceed in filling the matrix. So once your matrix is Z0 is available, then many of the things are already with you. Then you use the matrix equation there to solve for del A0. All the steps are illustrated here. So this is your Z0. Now you need to calculate Z transpose into Z0. You see that it is a 2 by 3. Ultimately, this multiplication will give you a 2 by 2 matrix. Okay. This is very simple to be determined as the matrix is so. The first row will be a simple sum of the squares of this element. Similarly, this row would be equal to sum of the squares of this element, and these two will be the product, sum of the product of these two. Is it okay? And this matrix is symmetric or non-symmetric?
So the multiplication matrix, that is symmetric.
Symmetric, sir.
Because you have very simple. Okay, if you have this type of matrix, what you need to, this element is nothing but you square all the element and add together. Okay, square it, because you have another, we will have another matrix there. that matrix will have an entry equal to 2212, 0.5276, 0.7135, 0.8262, something like this, isn't it? And that entry will be equal to 1947, something like this. Okay, so if you want to multiply this column with this row with this column, are not all the element will be squared?
Yes, sir.
So this is the sum of a square of your first column. This is the sum of a square of your second column. This is the sum of multiplication of the first column and second column.
Second column.
So these two are same. Also, it is a simple symmetric matrix. Okay, it needs a simple calculation. It needs 1 or about 5 or 10 seconds to do that. Okay. So when your matrix are available, then you have to take the inverse. It is a 2 by 2 matrix. You can easily take the inverse. But if your matrix is higher, actually, hand calculation is time consuming. Okay. In this case, in your exam, we will not give you something that needs, for example, hours to solve. But you can check it in your lab classes where you are doing your thing in MATLAB. So having this thing calculated, we can calculate D matrix. D matrix is the difference between your measured value and the value that you are obtaining using the value of A0 and A1. Then your D matrix is there. Now you multiply your Z inverse with D matrix. Then you solve for, this is what equal to del A. So once your del A is available with you, del A has two elements, isn't it? Del A equal to what? It is written in bold. This is matrix, okay? Column matrix is equal to del A0,
Del
del
A1.
So this is del A1. Once this thing is there, then you can update your del, update your next iterative value for your first coefficient will be equal to your
A0 plus del A0.
okay. Similarly, A1 will be equal to A10 plus del. Is not very interesting?
Yes,
Yes,
sir.
sir.
Very interesting.
But is it like in every iteration the value of del A will change?
Of course. Otherwise, not every iteration. It will change, but you have to stop it. Okay, what is your common understanding that will it be continuously changing?
No, sir. After a certain stage, it will stop.
Yes, because at a B, if you are going, if your algorithm is correct and proceeding in the approximation is what you call very prudently made, then what you can do, you can easily see that after a few iteration, that value of del A will be progressively actually decreasing. And you can, at every stage of your calculation that I have already talked about, you can check the error. Okay, your error criteria will always be given to you for iterative process. The reason is that if you want to determine the exact value of A0 for this problem, the value is they are given, then it will take, for example, very, very long time to converge. Okay. For this reason, if the say 10% error or 5% error is allowed, then whenever your A1 and A0 both will satisfy the conditions, then you can stop your calculation. Only a 5% allowance of 5% error may make your computational algorithm so efficient that it may need 1/10 of the iteration that is needed for zero error. Okay. Now the thing is that it is more interesting things are coming. This is what our actually the error equation. Okay, how many minutes do you have?
Sir,
10.
15 minutes, right? Roughly.
Like 11 minutes. Okay. Now already we started programming with MATLAB, and you know it, isn't it? What are you doing in your lab?
The Newton-Raphson method.
Newton-Raphson method. Okay, very good. Are you programming or just simply
Yes, sir.
calling
Yes,
the
sir.
root?
Yes, sir. We are programming, sir.
Yes,
You are
sir.
programming. Very good. Did you find any interest in it?
Yes, sir.
Okay, look. I usually say that because many of only few students are actually responding. But in my physical classes, because I didn't have any opportunity with you in our earlier days to in our physical classes. But you can share, have some experience from your seniors, okay? How I usually conduct my physical classes, okay? In my physical classes, actually, I always try to make my class live, okay? I always try to make my student speak. The reason is that if you do not want to speak, then your teachers are not almighty. Now you will just to read his mind, okay? They are not mind readers. For this reason, if you do not want to make your class live, then it will be very difficult for you to make your classroom interesting. Nowadays, we are having a very, very unfortunate situation, not in this country, but it is a global problem probably, that our students are making their classroom when it was physical was possible, less important. In my student life from class 1 to 12 classes, okay, whatever I learned in my classroom. Our classroom was so lively that we need not to do anything in the coaching classes or even after returning from home, we rarely open a book because our teachers were so caring that they always try to, for example, bring a cane with them. And if a student will not engage, they used to beat. But nowadays, if for example, a student is scholar in the classroom, their guardian will come and they will simply make chaos and eventually that teacher will be fired from this school. The reason is but in my days, school days, my father used to talk to my teachers that this is what you want, okay? In whatever ways you need to prepare him, you do it. And Alhamdulillah, we are very grateful to them, those who have introduced us at the very beginning of our life with many, many ideas, feelings, and values that we are still nurturing. So here in this case, you see that if you feel your thing interesting, you can program it. Programming is something like that, swimming, okay? For example, if you may have many, many texts with you that deals with techniques of swimming, okay, rules of swimming, something like that. And you studied, for example, in a university to get a master's degree in swimming. But you never, for example, go into the pond or a swimming pool to practice. So at one day you feel that I am a PhD of swimmer, so swimming. I have a PhD in swimming. So I will be going to Padma River for swimming. What will happen?
We will drown.
That means a very, unfortunately, there will be a very little chance for you to return. That is what the thing, okay? But if you learn swimming in practice, what will happen? You will never forget it. Even if you can move your arms and feet, then even if you are at 70, you could swim. Although you learned it when you were in your age was 5. So this is what the programming, okay? No matter in whatever you learn theoretically in your classroom, unless you program it by your own, you will never learn what is the, for example, beauty of programming, okay? Once you learn it, you will never forget it. You got my point? I learned my first programming when I was in the master's degree program, okay, in 1986 at where? Nobody introduced the thing to me in my classroom at that time because computers were not something like this that it was available to everywhere. Only in Bangladesh, only 3 or 4 organizations own computer. But whatever I did, I tried to self-learning something like some of my friends helped me. So what did happen? From that day, I started seeing my programming the computer. Still today, every day, I am with it. So try to build your habit in this way, okay? So if you have a programming with it, then I hope that you know how to declare a function. Do you know this?
Yes,
Yes,
sir.
sir.
we do.
Okay, fine. Now the thing is that in our understanding, what is it? But many of the things are not there. Okay, many people do not even people have computer that cost about 200,000 taka, but still they do not know how you computer. They are not. They do not know how to program by using a simple. They cannot use it by solving a simple engineering problem. But still, They are offering PhD, even masters, but they do not know how to program a single line. So this is what the thing. SR. Your SR is the function of what? In this particular program, is it not the function of
A0,
A0 and
A0
A1?
and A1. Yes, sir.
Fine. And that function is linear or non-linear?
Non-linear.
Non-linear.
Fine, non-linear, okay. Now consider that we have only 3 data points for our derivative, okay? Let us consider that we have only 3 data points, because if you want to write many things there, okay, let me use then things are there described, not in that way that I want to. Let me share whiteboard, okay? It will be good for you. Okay. So you see that our function is SR, that SR equal to what? Sum. In our case, let us consider that we have 3 data points, and this is equal to yi minus a0, 1 minus e to the power minus a1, xi, something like this, isn't it?
Yes, sir.
We have to square it. Then your SR function is developed in this way. Your SR would be equal to, say, y1 minus a0 into 1 minus e to the power minus a1 x1 squared plus y2 minus a0 1 minus e to the power minus a1 x2 squared plus y2 minus a0 1 minus e to the power minus a1 x3 squared, isn't it?
Yes, sir.
So the last one shouldn't be y3 minus a0.
Last term, sir, Y.
Okay, I hope you can correct it by your own. Hey, ঠিক করে নাও, ঠিক করে নাও, ঠিক করে নাও। ঠিক আছে, এটা 1 is okay.
Yes, sir.
Is it okay?
Yes, sir. It is okay now.
Then this function is a function of SR is the function of A0 into A1. Okay, what you need to do, you have to minimize it. By using some naive technique that we did it, okay, A0 equal to 0, then SR divided A1 equal to 0, we obtain 2 equations, isn't it? But if you want to go in this way, we will obtain some equation, but that cannot be solved so easily. But you can deploy a iterative technique to solve them. But here in this case, if you want to use computer, for example, your thing is what? You have to declare a function first, say a function. That function is, for example, say Z. So if you have a function, that function equal to Z, and you just give a name of the function, that function will have an argument to be called, say u. Why this is needed actually? In this function, your variable will be equal to a0 and a1, isn't it?
Yes, sir.
Yes, sir.
Okay, that variable should be initialized, or after solution, this should be returned. So you have to set your initial value, then you can, then this u will actually become an array. So your E1 would be equal to, say, this corresponds to your A0 and initial value, because you do not know the value of A0. And your U2 would be equal to what? Or you
A1
go in the
sir.
reverse way, actually. You have to go in the reverse way, because your assignment should be in the reverse way, reverse way, reverse way. Your assignment should be in the reverse way. Why? Hey, কোথায় গেল? Where or why? Because your value that using that function, you have to calculate the value of your unknown, isn't it?
Yes,
So
sir,
your
yes.
assignment should be in the reverse way, because you have to call this function by using 2 arguments. That argument will be passed, for example, these 2 values, a0 equal to, say, u1, and your a1 would be equal to u2.
U2.
Okay, after having this thing done, next thing is what? You have to find the function z. That z is equal to, is it not your SR?
Yes, sir.
Yes, sir.
So in this case, you just find it as your program definition is finished. Sorry. If your program definition is finished, next you can call a function that is there in your MATLAB. This function is called fmeans. Okay. If you call this function fmeans you will need two arguments. One argument will be the name of your function you are calling, and you have to call it by using two initial values. Say these two initial values should be put into this array. Your first initial value can be say a0, 0, and this initial value can be a1, 1. Okay. So if we just call this thing in this way, or even you can use the inline definition. Do you know what is inline definition?
Yes, sir.
So you can invoke this function to inline. Okay, that means this without writing this function, you can write the function inline. Then you call fmean. That if you call this fmean, you will see that fmean will give you the optimum value of your a0 and a1. Okay, so you complete the program. I will be happy to see if someone can tell me something in the next class.
Okay, sir.
But I usually do not give assignment. The reason is that I have very, very bad experience in it. I always try to instill with you your responsibility and your sense of responsibility, I would say. If you feel that these things are very important for you to explore, you have to engage yourself. But if you do not feel any important, then no matter how I do it, you will never look into it. You will simply copy it. So copying is the most disgraceful thing in my part. Please respond. 59.